of the past.
Part the weeds on any rock pool, and you open the curtains onto a life and death drama that has been played out for hundreds of millions of years. Some of the creatures that
Than we thought.
I think it's far more complicated than we thought.
we will investigate how they compete for food and space,
There are specialised tentacles simply for fighting.
and reveal the surprising behaviour they use to fight off predators.
It's really very agitated.
It becomes like a sort of animated mushroom.
This is the secret life of rock pools.
It's high tide, and the little world of the rock pool is connected to the greater world of the ocean beyond. It's a good place to be. There's normal salinity, there's plenty of oxygen, and above all, there's nutrients coming in from beyond. And yet it's not going to last for long. In a few hours, everything will change.
As the tide falls, life becomes very different for the creatures here. The exposed shore is now subject to unpredictable changes. Changes that depend on the weather, the time of year, and the time of day. Here, temperatures can range from freezing to baking. Oxygen levels fluctuate, and salinity can increase or decrease, causing body tissues to dehydrate or swell with water. But before any of these changes even begin to come into play, there is a more immediate problem. Dr. Mark Briffa of the University of Plymouth has come into the lab.
So, Mark, sea anemones are beautiful
Yes.
creatures, but most people might think that they're pretty inactive. They just sit there waiting for food to come along.
Yeah, well, they're relatively slow-moving animals, but they are animals, and that means that they have to consume food, and one of the things that sea anemones have to do before they can consume it is to capture their food. Can you see the feeding tentacles? There are 6... We can look at the use of the tentacles to trap food by taking a small piece of food, this is a little piece of limpet, and dropping it over the ring of tentacles. They kind of close in on it and put it down.
Oh, it
towards
likes
the
that.
mouth.
It likes that a lot. It's
Got a very hungry anemone here. And it's closing all of the tentacles, all 6 rings. It's closing them in to push the food back down towards its mouth. And they're not just for trapping prey either. In this species of sea anemone, there are specialised tentacles simply for fighting. And these specialised tentacles appear as little blue beadlets in a ring around the outside of the 6 rings of the feeding tentacles.
So hence the name, bead.
That's where it gets its name from, yeah. And they will use them in combat with rival anemones who are of the same species and therefore require exactly the same resources in terms of a good place in the rock pool.
Using a specialist time-lapse camera, we can speed these battles up to see what's really happening. Twisting their flexible bodies, anemones take aggressive swipes at each other, tearing off ribbons of skin. Losers have no choice but to find another place to settle. We may barely give anemones a second glance, but their remarkable fighting behaviour has allowed them to colonise the most sought-after locations in the rock pool, and has helped them thrive on our beaches for around 540 million years. Other creatures have dealt with the lack of space very differently. They have left the pools altogether, taking up residence on the rocks, where they are exposed at low tide. Around 530 million years ago, mollusks developed hard shells to house their soft body parts, creating a microclimate into which they could retreat.
And one of the first animals to do this is still with us. It's a living fossil, the chiton. The chiton has a number of plates which allow it to sort of shuffle around and grip tightly to the surface of the rock. But an even more effective way of doing this is under a single shell. And the mollusk that has done this most successfully is still with us in every rock pool and every rocky shore. It's the limpet.
Apart from clinging steadfastly to rocks, limpets play an important part in the ecology of the rocky shore. They too have to compete for resources. Professor Stephen Hawkins of the University of Southampton is a limpet expert.
And you might think, well, a limpet is a limpet is a limpet, but actually we've got 3 British species, isn't that right?
We do have 3 British species. We have, these are all Patella vulgata. And nearby we also have, that's a Patella depressa, which is a southern species of limpet, and it goes from sort of Senegal up to North Wales. And underneath here, I know there's a Patella aspera, and a Patella aspera have a nice hat of seaweeds on top of them.
Oh, and there it is.
And there it is.
I'm told that they vary in conicality according to where they are on the shore.
Yes, and also with age. I think as they get bigger and older, they tend to get more conical. And it makes quite a lot of sense to be conical like this because the circumference is where water gets lost when the tide's out. So there's more of an animal contained, there's more biomass contained within a more conical limpet than, say, a flatter one, like this sort of younger one.
What about hiding under these weeds?
Well, different species have different habits. Patella vulgata actually likes to shelter under seaweed. They can actually munch away at the bases of the seaweeds, and even by feeding at night, sort of gnaw away on the ends.
So what physiological adaptation allows limpets to hang on like the proverbial limpet?
They've got a big, extensive foot. You can see on this animal here. And essentially, it's a very complicated biological suction device. That's how it works.
And, I mean, I noticed most of the limpets, of course, seem to be on the rocks, but are they in the rock pools as well?
You do get some limpets in rock pools. The juveniles settle out of the plankton and actually settle in rock pools.
Oh, is that one there?
That's one there, yes.
Yeah.
And they get attracted by chemicals in the pink algae that are in this rock pool. It's a very good indication of what's a nice place to settle, and the limpets use these rock pools as a nursery ground for the first year or so of their lives.
And then they move up onto the barer rocks.
Yes, they move up, and they're quite vagrant when they're young, but once they get to about 15-20 millimetres, then they start actually homing on a fairly regular basis.
Surprisingly, limpets are territorial. They create a depression in the rock known as a home scar. As the tide starts to go down, they return to this place and hunker securely down. Territorial fights are common, and losers are prized off the rock.
Limpets are, I think they're really neat, and they're a great experimental animal to work with. They're so interesting, and they move, but they don't move too far, and you can do all sorts of things with them. I'm afraid I'm rather fond of limpets.
Well, I've become a fan too.
As the tide covers them, limpets leave their home scars and begin to feed. Limpets are very important grazers on the seashore. However, there is intense competition. To investigate further, we have to go back into the laboratory.
So, Stephen, you were up early this morning collecting us some limpets.
Yes, I collected these this morning at low tide, just as the tide was about to come over them. So we should be able to stimulate them to set off on their foraging excursions, to go off feeding if we put them in the tank.
It doesn't take long before they sense they're surrounded with water.
That's right. When the tide's out, they're on a home scar which they create in the rock, which their shell fits really well. One of the limpets is still on its home scar, but the other one's often and raised up.
Little tentacles coming out.
Yes, they have these fantastic sensory tentacles all the way around the edge of the shell. The big ones, the primary tentacles, actually match with those rays that you can see on the shell. Then there's smaller tentacles in between, and that gives lots of information about the physical and biological environment when they're out foraging.
And foraging means scraping algae and other things off the surface of the rock.
That's right, they feed by scraping the rock surface using their radula, yes.
The radula of the limpet is a ribbon-like tongue covered in teeth. It moves back and forth, scraping algal slime from the rocks. The limpet's radula is tipped with hematite, an extremely hard material that allows the limpets to graze on hard surfaces.
So what's the consequence of that?
Stephen's research has shown that limpets have a profound effect on the ecology of the seashore.
When they're off foraging, and this is where I fenced the rock to keep limpets out, and all the rest of the area here is where limpets were able to forage freely. And just 6 months later, yes, it's amazing, isn't it? Just 6 months later, there's a really dense growth of seaweeds, bladderwrack, fucoids, covering the rock in the absence of the limpet grazing. So basically the limpets, through their radula, they really control the algae.
Limpets are synonymous with rock pools, but through millions of years of evolution, they have pushed back the boundaries and have left the pools to colonize the rocks along the shore. The rising tide not only gives limpets an opportunity to feed, it brings with it danger. Starfish. Starfish belong to a phylum of animals called the echinoderms, which first appeared in the fossil record more than 500 million years ago. Starfish have macabre eating habits. Using their strong, sticky tube feet, they force open the shells of mollusks, and then, pushing their stomach out through their mouth, they digest the animal inside. Limpets have been locked in an arms race with starfish for millions of years and have evolved their own way of dealing with them.
So what are we looking for here?
Well, what happens usually is that the limpets get agitated when they sense a predator in the area, and then when the starfish is in contact with the limpet tends to raise up, and then it will often stamp down on the starfish and maybe drive it off. So let's see if that behaviour happens.
By a great battery of sort of wiggly tube feet. If I were the limpet, or
Didn't think they did
there he
this
goes.
behaviour.
Look at that.
It's really very agitated.
It becomes like a sort of animated mushroom in the end, doesn't it? Well, we can't say that rock pools lack drama.
I'll never look at limpets in the same way again. Beneath that implacable shell hides a strong personality. Unseen by us, their battles with starfish have been fought beneath the waves for millennia. But it is not just limpets that have to face predators. All the creatures in the rock pool must be constantly on their guard and have evolved many different ways of dealing with potential attackers from land and sea.
The majority of mollusks living around rock pools rely on their hard shells for protection against predators, but not all of them do so. This orange blob is actually a sea slug, and it's protected because it absorbs toxins from other sources, in this case the sponges that it eats. So in spite of its vulnerable appearance, it's actually rather well protected against predators.
In rock pools around the UK is unusual in that it is descended from terrestrial slugs. It is often found grazing out of the water, as well as the rock pools are sometimes visited by another mollusk. But this mollusk couldn't be more different from its relative, the sea slug. It is a fast-moving killer, the cuttlefish. Cuttlefish belong to a class of mollusks called cephalopods, and are widely considered to be the most intelligent of all invertebrates. I think they are the ultimate rock pool predator. At the Marine Biological Association in Plymouth, I have a great opportunity to get up close and personal with these magnificent animals. The ones here are kept for fisheries research and are easily trained to take food from my hand.
Wonderfully accurate vision, tentacles at the front, two of which I think are modified to grasp the prey.
They also have remarkable colour-changing abilities. This colour change is often used for camouflage, allowing them to sneak up on unsuspecting prey.
They're hiding in little tubes down there, which are obviously there for their comfort, so they can lurk. And when food comes around, well, out they pop. Now let's see if we can get the bigger one to come up this time. Come on, you know you want it. Whoa! Yeah. It winked me.
Cuttlefish are one of the largest predators to visit the rock pool. Some rock pool predators, though, are far less conspicuous, but no less deadly.
This is a dog whelk, a fearsome predator in the rock pools.
Unlike its limpet cousins, this carnivore has devised an ingenious way of hunting other mollusks. And one of its favourite prey are mussels. Mussels are filter feeders, sieving off the abundant food that drifts in the upper ocean. They attach themselves to the rock surface by strong threads, which they secrete through their muscular foot. These threads enable them to cling to the rocks, despite the relentless pounding of the ocean waves. However, the stationary mussel is an easy target for prowling dog whelks. Their radula is specially modified to drill through the shells to reach the soft flesh of the mussel. It's a gruesome attack. Mussels, however, can turn the tables on a dog whelk. Sensing a nearby attack, others in the colony start to produce more and more sticky threads. If they make contact, it can spell doom for the dog whelk, which will starve to death.
The hard shell of mollusks like the dog whelk persist long after the soft parts of the animal itself have decayed away. But these empty shells don't go to waste.
In the rock pool, when one species dies or moves on, another takes over. Empty shells are put to good use by one of my favourite rock pool creatures, hermit crabs. Hermit crabs use shells as a very effective defence against predators, and their bodies have evolved to fit them perfectly. Unlike other crabs, their abdomen has become soft and asymmetrical, and their back legs are very reduced, allowing them to fit inside shells. The asymmetry of their claws also allows them to close up the entrance to the shell as a defence against predators. The crab shell must not only be tough enough to withstand an attack, but must also afford it some camouflage. Dr. Mark Briffer from Plymouth University has returned to our lab to demonstrate how crabs go about choosing shells.
Well, nothing in nature is wasted, and that goes for our shells too, because here they are with a new occupant.
Because the common European hermit crab will get.
So these shells are obviously a protection.
That's right.
But are the crabs even choosier about which types of shells they pick up?
The crabs are incredibly choosy about what they want. They'll spend a lot of time and effort deciding whether to change shells, whether a potential new shell is a good one. I mean, they're also known to be particular about the colour of the shell, at least in terms of its contrast against the background. Can run a little experiment here. So what I have are two containers with a dark coloured substrate, and I have some Littorina obtusata shells. These are called citrina and dark reticulata. The only thing that's really different about them is the colour. Okay, what I'm going to do is place these shells so you can see straight away that, to our eyes at least, the citrina shells really stand out and the dark reticulata shells don't stand out so much. So I'm going to take 4 crabs in the citrina shells and give them the option to move into the empty black shells. Now, the other half of the experiment is to take 4 crabs in dark reticulata shells.
So I'll find those.
If you fish out 4 crabs in dark reticulata shells.
1, 2, 3, 4. There we go.
We'll put them into here. And these guys have the option of moving into citrina shells. So these crabs can move into shells that blend in, and these crabs can move into shells that stand out. Very particular about moving into new shells. They want to make sure that a new shell is absolutely better than the shell they're coming out of.
And I think he's going to come out. There he goes.
Swap shells,
He's
there we go.
swapped.
Gone from yellow into dark. And I can count here that 3 of the crabs are in dark shells in this dish.
And blending in well with the black
blending in well with the background.
Except for that stubborn one there, which of course is stayed obstinately in a yellow shell.
Right out against the background. I mean, maybe it hasn't made its decision yet. Maybe it hasn't spotted that shell stands out. It might have just got it wrong. What it shows overall, if we'd run this experiment lots and lots of times, the overall trend would be that significantly more crabs would be in the darker coloured shells. And that just goes to show how important blending into the background, or crypsis, is for these animals.
And it's not just camouflage that's important as a defence against predators. The shell must also fit well if it is to give the crab the best chance of survival. Because of this, there is intense competition for shells.
OK, so here we are. These crabs have been isolated for about 16 hours. We're going to use this tank as an arena to stage a fight in. And this large crab is in a shell that's too small for him.
So it's uncomfortable.
Yeah, you can see he doesn't really fit in there very well. He's trying to withdraw, but there's still, the claws are exposed. So let's put him in there. This is a smaller crab, And you can see he's withdrawing right
So
into that shell.
he's shaking around in a rather loose coat.
Well, he's got a very, very spacious house. So we've got a big crab in a shell that's too small and a little crab in a shell that is just right for the big crab.
A large crab adopts intimidation tactics in an attempt to make the smaller crab leave its shell.
It's a little bit like a war of attrition, you know, who can keep going for the longest? Will the attacker wear itself out of the shell wrapping before the defender decides to give up? If you can, here we go.
Here we go.
Yay, an eviction. There it will say the attacking crab just evicted the defending crab. The attacking crab has gone into the shell that's just pulled the defending crab out of, and it's trying to keep the defending crab out. No, the defending crab has now gone in to the shell that the attacking crab vacated.
Not putting up much of a fight, I have to say.
Well, you're not going to hang around without a shell if you can possibly avoid it.
Hermit crabs are an evolutionary marvel, perfectly adapted to recycle the discards of another species as a defense against predators. As well as competing for space and avoiding attack, other creatures have evolved remarkable adaptations to deal with the ever-changing environment.
Well, the tide's now really out, and this place has become quite a hostile environment. Everything's drying out. You'd think that any organism with any sense would have retreated out to sea with the ebbing tide, and yet, hiding away here is something really extraordinary.
Before the tide retreats, timing it wrong could be fatal. Anticipating tidal change is a problem all rock pool creatures face. Dr. David Wilcoxon of the University of Aberystwyth is going to show me how animals are adapted to cope with this.
So the tide is out, and the question is, how do the organisms on the beach know when it's coming in?
That's actually a very good question, because all organisms, including ourselves, have biological clocks which enable us to anticipate changes in our environment, such as night and day, and in this case, the incoming and outgoing of the tides. And this organism we have buzzing around in these tanks is a marine equivalent of the woodlouse. It's an animal called Eurydice pulchra. And Eurydice has a very, very good 12.4-hour or tidal clock, whereas ours is run on a 24-hour basis. But they come out of the sand and swim when the tide is in, and feed and breed. And then what they'll do before the tide goes out, they'll actually bury back into the sand, so they maintain their position on the shore, their preferred position on the shore.
And as we have seen, maintaining the best position on the shore is essential for survival. To best illustrate tidal rhythms, David has devised a unique experiment.
So what we have here, Richard, is activity monitors, and in each tube is a little bit of sand and some seawater. And there's an individual Eurydice in each of these tubes, and they're all inactive at the moment because currently they're expecting it to be low water. When they expect high water, they'll start to swim, and across each tube is a little infrared beam. And when they swim through that beam, the beam is broken, and the beam break is recorded on the computer.
I see.
We can actually turn those recordings into plots so we can visualize their activity. And this is a plot from one individual Eurydice. And you can see these black bars here represent beam breaks or activity periods. And these bouts of activity are occurring every 12.4 hours.
On the nail.
A very precise 12.4-hour rhythm. And so we can actually show they have a tidal rhythm. And the important thing is that this rhythm will continue in the absence of any tides.
The tide outside has now risen, and there is a definite change in activity of our subjects.
Well, there's an amazing sight.
It's been a few hours since we looked at them last, and we can see now they think it's high tide, or they're expecting it to be high tide, and they're zooming up and down, crossing the infrared beam.
I can see the numbers going up.
That's right, and those beam breaks are being recorded on the monitor here.
So in nature, this is when they'd be feeding and on the hunt.
That's right, yeah.
But obviously this internal clock needs some controls on it. I mean, are there things in the natural environment that help set those controls?
There are. What happens is that each individual animal, its clock will be slightly different to the next one, and the clocks drift what we call out of phase with the natural cycle if we remove it from its natural environment. So the incoming and outgoing tide actually resets their clock. It resynchronises their clock.
Life in rock pools is more complicated than we thought.
I think it's far more complicated than we thought, yes.
The ability to anticipate the changing tide is essential. Knowing when to feed, breed or hide is vital for any creature living on the shore. As the tide changes, so do conditions on the beach. And this has a profound effect on all living things, even the seaweeds.
For more than 1 billion years, life on Earth was dominated by very simple single-celled organisms. Slime, if you like. This rock's covered in it. But those organisms included photosynthesizing blue-green bacteria called cyanobacteria that form living films and breathed oxygen into the atmosphere, thereby transforming the early Earth. And about 1.3 billion years ago, they were joined by much larger multicelled organisms, algae, doing the same job, still photosynthetic, but these today dominate what we see on the beach and in the rock pools. Of course, most people know it simply as seaweed.
With more than 9,000 species of seaweed in the UK alone, the sheer variety and volume of them is staggering. 1/4 of the total global energy captured by photosynthesis is fixed here in the intertidal zone. So seaweeds are the basis of a rich and complex food chain. Seaweeds show a distinct pattern of colonization from the upper to the lower shore. This is known as zonation and gives us a visual indication of how conditions vary. But what causes zonation, and why is it important? Professor Colin Brownlee of the Marine Biological Association is going to demonstrate.
These seaweeds grow on the rocks, as you know, and they produce eggs and sperm, just like animals. And they're produced into the seawater, and the eggs are fertilized by the sperm. And what they want to do is sink to the rock surface and then attach where they can grow.
We can analyze a sample of seawater under the microscope.
So what can we see here?
The large round cells are the eggs. Each one of those is a single egg. And all of those small little creatures swimming around them are the sperm.
Over the next day, the fertilized eggs develop into embryos.
So this is what they look like after about 24 hours. You can see that they're no longer spherical eggs.
It's a pear-shaped
It's a pear-shaped embryo, and it's protruded a little, we call it a rhizoid. It's a tiny little root.
All seaweeds get a chance to colonize the beach, but one factor deciding survival is rainfall. Remarkably, fresh rainwater can kill some seaweed embryos.
And we can actually try to demonstrate that now, just by adding some dilute seawater to this dish. So it's wobbling a bit as I add it.
It's twitching, it doesn't look very comfortable.
That's me dropping the water onto it. There we go.
Good Lord.
That's dead.
That is one seaweed less.
Fresh water penetrates the cells by osmosis, causing them to swell and burst.
And the difference between different species in how they swell really determines where they can survive on that shore.
So there is a constant bombardment of microscopic seaweed embryos upon the shore, and order is only maintained by relative salinity. Seaweeds provide food and shelter for many other creatures. They are the basis upon which much life in the rock pool depends. The rock pools highest up the beach are exposed to the air for the longest. Sunshine causes evaporation that in turn causes the salinity of the pools to increase and the temperature to rise. Oxygen can fluctuate throughout the day and night. Here, everything is pushed to its very limit. Most active animals choose to abandon the highest rock pools. But one of our rock pool favourites has evolved a unique biology that has allowed it to survive further up the shore.
Crabs are arthropods, which means they have jointed legs, as well as this hard exoskeleton which encloses their body. It allows them to tolerate conditions that other animals might find difficult. Of course, arthropods have been around for a very long time. In fact, my own favourite organism, the trilobite, is an arthropod, sadly long extinct. They died out about 250 million years ago, but their relatives, the crustaceans, prospered. And it has to be said that if you have an exoskeleton, you also have one particular drawback. If you want to grow, you have to molt, and then you're vulnerable.
Prior to molting, a crab secretes enzymes to separate the old shell from the underlying skin. The crab then absorbs seawater, causing the old shell to come apart at a seam that runs around the body. The carapace then opens up like a lid, and the crab extracts itself from the old shell. At this time, crabs are extremely vulnerable and will usually hide. But molting is also essential for another function.
Crabs don't just need to molt when they want to get larger, they also have to molt when they want to mate.
To investigate this further, I have invited Dr. David Wilcoxon back into the lab.
David, what's going on?
Well, Richard, the female crab has to be soft. She has to just molted in order for the male to transfer sperm.
So that's a soft-shelled crab
That's
stage.
right, yeah. So she's very vulnerable at this stage. She's quite immobile. She's very soft and makes a nice meal for a predator, for example. So the male crab will actually guard her. He'll embrace her like this. And the female opens her abdomen. It's the flap on the underside of her body. And the male also opens his abdomen, and they transfer sperm through a pair of modified legs from the male. The male will detect the fact that she's coming into molt because she releases pheromones, and he'll guard her, he'll stand over her and cradle her. When she molts, he then flips her over and they copulate. And he will continue to guard her for quite a number of days, maybe up to 10 days or more.
So if anybody finds a pair of crabs like this, the message is, put them back.
Absolutely, yes. So I can actually show you a neat trick here in the lab with the pheromone from females. I've got here some water that I've collected from an aquarium that's contained female crabs that are coming into molt. And I've got an inanimate stone here, an air stone from an aquarium. And if I drop that into a tank over here, we might be able to see the male crab responses.
Right.
So he's scented the stone,
And,
okay, and he's up on tiptoes.
tippy toes are characteristic.
Starting to cradle. Ooh, he's definitely attracted to it.
Oh dear, poor crab. Fancy having a piece of stone for a partner.
Of course, this is all driven by the pheromone, this behaviour.
This strong reaction to the scent a female gives off when she molts changes the male from potential attacker to defender. This is vital if crabs are ever going to mate.
So what happens next is the question.
So the male crab has transferred his sperm to the female, and the female will now produce eggs, which are fertilised. And if I can just disturb them gently.
Not very keen to be disturbed. Oh. Not keen at all, really.
So we can see, I'm trying not to take them apart, but the female abdomen is open there, and underneath there, she will produce a very big mass of eggs. We call them buried females.
The eggs females carry look like small round berries. They can carry this egg mass for several months. They eventually develop into free-swimming larvae, which feed among the plankton for up to 3 years, before settling on the seabed as juvenile crabs.
So you may find what you think is a buried female on the shore, but actually it may not be. And I've got something really quite interesting over here that I found earlier. I'll show you.
Sounds intriguing.
So this is a shore crab again. If I can just pick it up, okay. And on the underside, we have what appears to be an egg mass. It looks like a buried female, doesn't it? But in actual fact, if we look more closely, this is a male crab. And this egg mass is actually a parasitic barnacle.
Well, how on earth do you know that?
Well, we know it's a barnacle only because of its larval stage. It has the same larvae as all the other types of
This
barnacles.
is only a millimetre or two long, isn't it?
Very, very small, yeah. And the larvae actually penetrate into the body of the crab and sends out the rootlets into the body parts and absorbs nutrients from the crab. It takes over the crab.
Oh, it's like something out of Alien. It's converting the crab into a kind of machine for producing more parasitic
That's right. and
barnacles.
That's exactly what that egg mass there is.
After the invasion of Saculina, the crab is unable to perform its normal function of molting. Saculina interferes with the male crab's hormones. It becomes sterile and even begins to behave like a female.
Well, it's hard to believe that really such a, frankly, rather disgusting creature is related to the most abundant things that we find on practically every shore, the regular barnacles.
It's very different, yeah.
Crabs are a rock pooling favourite, but few can imagine how complex and interesting their world really is. As well as their fascinating reproductive cycle, crabs have evolved to thrive in some of the most extreme environments on the rocky shore. To explore the lengths some animals will go in order to survive in the most extreme conditions of the rock pool, I'm going on a little adventure. Something I've never done before. Night rock pooling with Dr. John Spicer of Plymouth University.
I think at night it's more exciting because things happen much more quickly. There's a lot going on. And if you've just got a little bit of patience, you can see just so much. Even in a small pool like this, it is a busy, violent, exciting place. I mean, one of the really nice things about night is the fact that even animals which would normally be submerged, because it's quite humid at night, will come out and they will scuttle across the rocks. For instance, if you look really carefully, you can see the shadows of little crabs as they run from crevice to crevice. They're no longer in the water, but as long as they're damp, their gills are such that they can still breathe when they're out of water. But I mean, although this is good news, this is water when the water's gone. It's a little refuge, you know, a little sea, but it's still got its own problems. At night, the plants are no longer photosynthesizing. The plants and animals are using the oxygen, and so the oxygen declines and throughout the night, sometimes down to zero.
So you might actually finish up with somewhere that's extremely unpleasant for life.
It's one of the prices of staying hydrated. You have to put up with real severe extremes of oxygen. Okay, so I think if I take some water from this rock pool, which should be quite low in oxygen, we can take it back to the laboratory and we can actually use it in the laboratory and see the response of some of the creatures that live here to that low oxygen water.
Oh, there's plenty of water in there.
Just don't spill it. So Richard, what I'm going to do is actually here in the laboratory try and set up a little experiment with 2 artificial rock pools.
And which species are we using?
Now, the animal we will use is a thing called Palaemon elegans, which sounds a very grand name. It's a common glass shrimp.
Ah.
Where you can see all the inner working parts. Very beautiful.
And you're pouring the water in slowly, I guess, because you don't want to alter the oxygen.
That's right. I mean, the oxygen will alter by itself, but if we do it nice and slowly, it should take a while to alter. That's great. Now we'll bring the shrimp across. Here they are, Palaemon elegans, relatives of the common prawn. This one used to be fished commercially off Britain, or at least its big brother did. These particular shrimps you only really find intertidally in tide pools.
And they're the ones you often see almost colourless against the sand.
That's right, they can change
Hard to
colour.
see.
Yeah, they can change colour. I mean, within a few minutes.
Quite busy at the moment.
They're normally extremely active animals, and we just have to leave them to settle down a bit now and see what happens.
Because it is found in the higher rock pools where the biggest changes in oxygen occur, the glass shrimp has evolved a unique behaviour that we can see in the laboratory.
You'll notice that it's now crawled onto the rock here, and by lying on its side it has a partial immersion response. It's not totally out of the water, so it's actually making oxygen come into the water by beating its back limbs. And also inside its gill chamber, it's got a little device called a scaphognathite, which is beating and oxygenating the water. Now, if it was totally out of the water, the gills would collapse and it suffocates. If it stays in the water, it suffocates. This partial immersion response
is a way of keeping alive in a time of crisis.
That's exactly right. That's exactly right. It's closely related. Deeper water relative, Palaemon serratus, doesn't do this behaviour.
So this guy is able to survive for longer in shallower and more challenged rock pools than its close relative.
That's right, that's exactly right. And we see that on the shore. You go to the middle lower shore, you get both species, the high shore, and it's only this one.
So it's a tough little beast.
It is this sort of ingenious behaviour that makes rock pool creatures so resilient to the extremes of the intertidal environment. They've risen to every challenge that has been thrown at them. Through geological history, some of these animals have survived global catastrophes that have wiped out much of life on Earth. With their physiological and behavioural adaptations, they have had what it takes to endure. But what does the future hold for them?
The tide's almost in, but there's still some animals that can survive having been out of water for more than half the day. And the last, toughest ones are barnacles. And when the sea finally splashes open them, they'll feed at last, extracting all their nutrients in just an hour or two in the whole day.
Like all intertidal animals, barnacles have to deal with fluctuating conditions on both a daily and seasonal basis. However, recent research suggests that barnacles and other creatures have to cope with changes over a much bigger time scale, changes that we may be responsible for. Nova Mishkoshka of the Marine Biological Association has been analysing long-term data on barnacles here in Devon.
Well, if you don't know barnacles very well, it has to be said that they do all look rather alike. But when you do know barnacles well, like you know that there are subtle differences between species here, and that those species differences are connected to climate change. Is that right?
Yes, we've found over the many decades that we've been studying barnacles all around the UK, but especially down in the southwest here, that the warm water barnacles, which you can see around here with slightly more greenish tinges, they're kite-shaped. These warm water barnacles have become a lot more abundant, especially over the last 20-25 years since climate change really started to take hold. Their northern limits are in Scotland of the warm water barnacles, and they go all the way down south past the Mediterranean and slightly into North Africa. Whereas the cold water barnacles,
which are?
These are the ones that they're slightly whiter. Here's one you can see. This is Semibalanus balanoides.
Oh,
here.
I can see it now. Yes, it takes. You have to get your eye in, don't you?
Their northern limits go way up into the Arctic Circle, but their southern limits have been cut back and back further north. They used to be in northern Spain and around the Bay of Biscay region, where there's been a big trimming northwards because it's just plainly too warm for them to live there anymore. And we're even seeing the effects here in the southwest. We've seen a massive decline in the survival of these cold water barnacles.
Do they get bigger than this, or is this kind of their usual size?
This is quite a representative size. However, when you find shores further up north with just the cold water species, Semibarnus balanoides can grow quite large. In its first 6 months, it can grow significantly bigger than the warm water cathamids do. So given an opportunity, it can increase its size quite rapidly.
And have we got their natural predators dotted around on the surface?
Yes, you can see that we've got some marauding dog whelks, and these dog whelks do preferentially eat the cold water barnacles, Semibarnus balanoides. So it'll be very interesting to see whether, when we lose these for good in the southwest, whether the dog whelks will actually be able to change and then feed entirely on the warm water barnacle or not.
Well, I guess the story of evolution is often change or die.
Yes.
It is alarming to think that we might be responsible for affecting the survival of the creatures we know and love so well. However, because they have adapted to one of the toughest places on Earth, rock pool animals have outlived many other species they shared the seas with, including my favourites, the trilobites. As a paleontologist, I marvel to think that their ancestors lived alongside fossil species I have studied, but whose lives I can only really imagine. And rock pool animals may well...
Here on Oronsay, in the Western Isles of Scotland, the whole hill behind me is a shell midden. Our ancestors, 7,000 years ago or more, collected huge numbers of limpets and some cockles that became a staple part of their...
Planet Earth 2 continues tomorrow night at 8 with David Attenborough's attention on the jungle dwellers. Now, Katie Derham takes us on a musical journey on the trail of the girl from Ipanema, Brazil, bossa nova and the beach next.